Alright, so this video is going to be over some common acids and bases as well as Lewis acid base chemistry. So some common acids and bases: HCl, HBr, HI, sulfuric acid. These are some common strong acids from general chemistry. They're also known as inorganic acids. I mean, this is organic chemistry, right? So, but these are obviously used very often, and that brings up organic acids, right? And so these are the carbon-containing acids that we see quite often, such as acetic acid, which has a pKa of 4.8. This, remember, acetic acid is also pretty much vinegar. Okay, and then we've got this guy right here, which is pretty fancy. We've got it's similar to sulfuric acid in that it's got a sulfur in there with an OH on it. It's got a pK of -7, and it's abbreviated as TSOH, and the name of it is p-toluene sulfonic acid. That P stands for para, so it's para-toluene sulfonic acid. And organic acids are also found in things like kombucha or coffee. I mean, specifically acetic acid, that is vinegar, right? So if you've ever had kombucha, it's fermented tea, and that's exactly what it's bubbly vinegar water. It's actually super yummy, definitely an acquired taste. But coffee as well, and then aspirin, which you are, I'm sure, familiar with as well. These are all going to contain organic acids, and they play an instrumental part in either their effectiveness as a drug or as their flavor, which is why acid-base chemistry is really important, but also really interesting. And so let's bring up some common bases. You've obviously seen a few already, but you are, just as a refresher, sodium plus, that's the spectator or that's the spectator ion or counter cation. We have a sodium plus, potassium plus, lithium plus. Those can be coupled with hydroxide ions, which is OH minus. We can also have any of them coupled with OCH3 minus, which is a methoxide ion. Again, could be coupled with ethoxide, which is OCH2CH3 minus. Or we could have something that's really common and also really important. You should get to know this structure really well. This is called Tertbutoxide, and it's OC in parentheses CH3 subscript 3. Okay, so let me draw this structure out for you so you're familiar with what it looks like. But we got that negative charge on the oxygen bound to the carbon, with 3 methyl groups coming off of that carbon. So this is again called tertbutoxide, and it is a very strong base, but it's also really big and bulky too. So this is going to be important in some important chemistry that we talk about in a few chapters from now. So NH2 minus, we introduced this before, but it is an amide. So oftentimes you'll see it as NaNH2. Okay, don't get this confused with NH3, ammonia. So we've got another amine. This is N, and then we've got a couple parentheses in there, right? But CH and then CH3 subscript 2, all of that with a subscript 2. So this is called diisopropyl amide. And this is also a really common base that's kind of huge, big, and bulky, and plays an important role later on in the book, or in this course rather. So H with the lone pair that gives it a negative charge, this is called a hydride. Typically what you'll see is sodium hydride, so sodium countercation with that, but you could see lithium or potassium hydride as well. Now, again, it's kind of important to note that all strong bases have a negative charge, but that doesn't mean that all negatively charged species are strong bases, right? And we kind of see this with like the acetic acid giving us an acetate. Acetate's not a very strong base, but then we also see it with fluoride ion, chloride, bromide, and iodide. So these guys are very weak bases, and we can think about it as the stability of those conjugate bases, right? It's pretty good, but remember the concept of a strong acid produces a weak conjugate base, and so HCl is a strong acid, for example, and therefore the chloride anion, which is the conjugate base, is weak. So that's just an example of how not all negatively charged species are strong bases. Moving on to another common base is a carbanion. Here's a generic version of one. These are really strong because carbon doesn't like to be negative. It's not very electronegative. And a common example of that would be butyl lithium. So this is actually a pyrophoric species, and it will just light on fire when exposed to air. Tertbutoxide is very similar, but it's actually even more pyrophoric, more reactive with water in the atmosphere, and it does actually kind of, if you squirt it out of a syringe, it does kind of make that flame that you see in that GIF. It's really strong and very dangerous. Weaker but common bases are triethylamine as well as pyridine. So get familiar with these as well, because they will pop up, and it's important that you know what their role is when you see them in a chemical reaction. So Lewis acids and bases. What are they? You should remember this from general chemistry, but if you don't, that's fine. We'll learn them, and it's very straightforward. So a Lewis acid is basically an electron pair acceptor, and it's important to note that all Bronsted-Lowry acids are Lewis acids, but not all Lewis acids are Bronsted-Lowry acids. Because remember, Bronsted-Lowry means that they have to be a proton donor. So Lewis bases are electron pair donors. Okay. So all Bronsted-Lowry bases are Lewis bases, but they attack different things. Okay. So Bronsted-Lowry bases are they donate electrons, or their electron pair, to protons always, but the Lewis base donates to pretty much anything that's electron deficient. Okay, and so that's the distinct difference between a Lewis base and a Bronsted-Lowry base. Again, the Lewis base donates to anything that's electron deficient, right? All right, so some examples of Lewis acids that are not Bronsted-Lowry acids are the aluminum chloride and the boron as well. So remember, these are sp2 hybridized, and so they have a vacant p orbital, and therefore are electron deficient because they don't have an octet. Okay, so these are Lewis acids that are electron deficient, and they are also not Bronsted-Lowry acids like water or acetic acid would be. Some Lewis bases are hydroxide, methanol, or ethylene, and ethylene has got the extra bond in there, that pi bond. That's where the electron richness comes from, and for water it's got those lone pairs, so it's electron rich as well, and the same can go for methanol. Even though they're not negatively charged, they are electron rich. So some Lewis acid base adducts. So a Lewis base, being electron rich, attacks the Lewis acid, and it forms something called a Lewis acid base adduct, meaning it's basically just a chemical bond between the two. So water, being the Lewis base, attacks the boron trifluoride. It's got a vacant p orbital, right? And so the lone pair on the oxygen of water can form a bond with the boron, and we get this particular adduct where the oxygen is positively charged, it's an oxonium, and the boron is negatively charged. So it's important to define a few things. These terms are pretty much what we'll be using throughout the course, and that is nucleophile and electrophile. A nucleophile means nucleus loving, and electrophile means electron loving. So, I mean, I hate to say it, but just think about like a pedophile. They love little kids, and that's what philia is. So the suffix for nucleophile and electrophile, it just means to love something. And so they love a nucleus and they love electrons. And so these terms are going to be, again, they are going to be used throughout the course. And so it's really important that you become familiar with them and then know that a nucleophile is an electron-rich species while the electrophile is an electron-poor species. Okay? And you could also call them the Lewis base and the Lewis acid, respectively. So, looking at this next problem. So we've got a bromide ion with a carbocation, and they come together, right? So the Lewis base, which is the bromide ion, is electron rich, and it attacks an electron deficient species, which is the carbocation. That's a carbon with a positive charge. We don't want a positive charge on oxygen, and so it wants electrons from somewhere. Might as well get it from that bromide ion that is very electron rich. And so we end up getting that product on the right. And this is a really common Lewis acid base reaction, but at this point we would just call them the nucleophile and the electrophile. Electrophiles are going to be positively charged or have a delta positive charge on them, while the nucleophile could be negatively charged or just have a lone pair on it. Okay, so remember that. Alright, so let's take a look at another example. We've got this structure here. And again, this is pretty much just an introduction to something that we'll see later on in the course. But we have this aluminum species here. Remember, aluminum is drawn in blue because it's electron deficient. It is the Lewis acid, while the chloroethane is drawn in red because it is technically the electron-rich species, and it can attack the vacant p orbital on the aluminum to form that acid-base adduct on the right. Okay, and then we get a positive charge on the chlorine and a negative charge on the aluminum. All right, so this is going to be very common. Familiarize yourself with it, and it is intuitive once you can come to the conclusion that what an electron species, what an electron-rich species is, and what an electron-deficient species is. Then you just jam the two together, and that's chemistry. So, which is the Lewis acid and which is the Lewis base of this? So the left species is cyclohexene, the other one's hydrochloric acid, so you should be able to get it. Lewis acid is the hydrochloric acid, right? Therefore, process of elimination, cyclohexene is the Lewis base. And don't forget, there are hydrogens at that alkene position, that double bond. And the product is what we see on the right. Okay, so how does this form? Well, remember the hydrogen is delta positive, and it ends up on that's the blue hydrogen on the right in the product. The double bond I drew in red because that is the electron-rich Lewis base. And what does the Lewis base do? It attacks electron-deficient species, and that is the H plus in this case, and that forms the product on the right. Remember, we also want to maintain charge on the left and the right, And notice there's no net charge on the left, and there's also no net charge on the right because the carbocation is canceled out with that chloride ion. So let's get some practice. Label the Lewis acid and the Lewis base. Use curved arrow notation to show the movement to electron pairs. Now remember, basically what you want to do is just pause the video after I've drawn out the problem and then try it out yourself, and then see if you can get the same thing. So we got this ketone on the left with hydronium ion, and then we've got our products on the right. It's oxygen with 3 bonds and a positive charge is called an oxonium ion, and then we've also got water. So we want to label the Lewis acid in the base and then use curved arrow notation. So hydronium ion we know is H3O+, that's the acid, right? So that means that the ketone, the one on the left, should be the Lewis base. And I've labeled all those hydrogens as blue because those are all susceptible to nucleophilic attack. So attack from the Lewis base. And you end up getting what you get on the right side with the oxonium or the hydrogen on that carbonyl CO. Okay, I'm throwing out a bunch of terms for you because I want you to hear them as we come across them, and you'll become more familiar with them as we go along. So, draw the products of each acid-base reaction. So here we've got a benzene ring with an OCH3 on it, and that's fused with another ring with this guy hanging off. Okay, so basically we've got a carboxylic acid. That's that CO double bond with the COH on there, and we've got a sodium hydroxide. We know hydroxide's a base. We know carboxylic acids are the acid. They got that resonance stabilization. That hydroxide attacks that proton, and then we've got resonance stabilization. You don't necessarily have to draw that resonance stabilization immediately, but it is a very common practice to show that. And so rather than putting the negative charge right on that oxygen that the blue hydrogen is bound to, you typically draw the resonance and put that negative charge on the other oxygen. Whoops, sorry. Let's put that double bond there instead. Finish the rest of the structure. And that's one of the products. And then we also have water as our other product of this acid-base reaction. Alright, let's take a look at another one. So again, it's a benzene ring with a CF3 on there. That's usually called a trifluoromethane. And then we've got this other group dangling off, and HCl. Okay, so nitrogen with the lone pair, that's typically going to be a base, especially in the presence of HCl, which is hydrochloric acid. Remember, the Lewis base attacks the Lewis acid, and that gives us our basically the blue hydrogen is transferred to the nitrogen, and now that it used its lone pair to create that NH bond. So since it has 3 bonds already and it forms that NH bond, that's 4 bonds to nitrogen, creating an ammonium group and a positive charge on that nitrogen. And then we also have our chloride ion. Okay, so moving on to the next problem. Which of the following anions is the strongest base? Okay, so in order to really grasp the concepts, you should be able to explain your choice as well. So let's write it out, and then again, pause the video and then try it on your own. Let's see what you get. So compound X and then compound Y on the right. We have the negative charge on two different locations of this more or less the same molecule, right? So which one is the stronger base though? So we want to look at which one is more stable. Remember the concepts of stabilization of the conjugate base? We can apply those here. They're both bound to a carbon, so they're both carbanions. That's not really going to, that's the element effect. And so now what we want to do is compare the stability using element effects, resonance, inductive effects, as well as hybridization, or like what orbital it's on. So the element effect is out. Resonance stabilization is present in X, but is not present in Y. So since X is stabilized, that means it's lower in energy and is a weaker base. So Y is therefore the stronger base because it does not have resonance stabilization. Okay. All right. So I actually like that problem. It's pretty fun. And it just requires you to think a little bit more because we always talk about acid strength, and so keep that in mind. So write a stepwise sequence, reaction sequence, using proton transfer reactions to show how we get from one product to the other. Okay, so the following reaction occurs, and so we have a hint here in this problem, and that's as a first step, use a hydroxide to remove a proton from the CH2 group between the CO and the CH2. I'm sorry, and the CC. We have a CH2 group. So let's draw it out and then let's see what happens. So this is a difficult problem. That's why I'm doing it here, because I want you to get exposed to those difficult problems and also think about them too, because remember, you got to pause the video and then try the problem. Okay, so use the hydroxide to remove a proton from CH2 group between the CO and the CC. So let's draw those protons out. We can't forget that they're there. The hydroxide is highlighted in red. That is our base. And we'll draw these protons in blue because those are the acidic protons. Okay, so once we remove that proton, as the hint indicates, we can draw the negative charge on that carbon, giving us a new carbanion. Okay. And remember, this is an acid-base reaction, so it's technically an equilibrium. And we've got one hydrogen on there and negative charge with that lone pair on there, right? Now, this particular carbanion is resonance stabilized, so we can draw a resonance structure. Sorry, I messed up and put the wrong arrow. Classic. We need that resonance arrow here. I wasn't thinking. And this is our resonance structure. So now that we've got that, we can also draw another resonance structure where we put the negative charge not on the oxygen or the adjacent carbon, but on the carbon at the very bottom of that molecule. So basically all we're doing again is shuffling pi electrons. That's what resonance is. And so we need to be aware of this. So if we have alternating double bonds, so it goes double bond, single bond, double bond, that's definitely room for resonance right there, okay? And so then once we have that carbanion on the bottom, we can that's a base, right? It's a very strong base, a carbanion. And so the solvent is water, and so that carbanion can just grab a proton from water, and then you get the final product. I drew out the red bond, the blue hydrogen, and all the other hydrogens, just so you can see what the final product is. And so that's pretty much it. This is a good chapter, and so make sure you get your practice in the acid-base chemistry.